এনার্জি বা শক্তি, আসলে শক্তি আমাদের দৈনন্দিন জীবনে কতটা গুরুত্বপূর্ণ তা আমরা প্রতিনিয়ত ফিল করতে পারি, কিন্তু প্রশ্ন হচ্ছে পৃথিবীর এত এত এনার্জির সোর্সটা কি? আমরা পূর্ণিমা রাতে চাঁদের সৌন্দর্য দেখে অত্যন্ত মোহিত হই, কিন্তু প্রশ্ন হচ্ছে চাঁদের এত সৌন্দর্যের পেছনে রহস্যটা কি? এসব প্রশ্নের উত্তর যদি আমরা দিতে চাই তাহলে একটা কথাই বলতে হয়, সেটা হচ্ছে সূর্য। সবাইকে ওয়েলকাম করছি যশোর বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয় জামালুল ইসলাম অ্যাস্ট্রোনমি ক্লাবের অফিসিয়াল ফেসবুক পেজ থেকে। আমরা আছি সিক্সথ ওয়েবিনারে। আমরা আজকে যে বিষয়টা নিয়ে আলোচনা করব সেটা হচ্ছে স্টাডি অফ দ্য সান থ্রু অ্যাটমস, অর্থাৎ সূর্যকে জানতে গিয়ে আমরা একেবারে অ্যাটমিক লেভেলে চলে যাব, যেতে পারি সাব অ্যাটমিক লেভেলে, ইলেকট্রন, প্রোটন, নিউট্রন বা কোয়ার্কসে। কিন্তু বিষয়টা হচ্ছে যে হয়তো আমরা টাইম ট্রাভেল করব না, এখান থেকে সায়েন্সের বদৌলতে আমরা সূর্যকে জানার চেষ্টা করব। ঠিক অ্যাটমিক লেভেল থেকে আমাদের যাত্রাটা শুরু হবে এবং বর্তমানে সূর্যের এই অবস্থাতে আমরা জার্নিটা করব। এই জার্নিতে আমাদের সাথে যিনি সারথি হয়েছেন, আমাদের অত্যন্ত সম্মানিত শ্রদ্ধেয় অতিথি প্রফেসর সুলতানা এন নাহার। উনি এই মুহূর্তে রয়েছেন ডিপার্টমেন্ট অফ অ্যাস্ট্রোনমিতে, দ্য ইউনিভার্সিটি, ইউনাইটেড স্টেট অফ আমেরিকাতে। এবং উনি ঢাকা ইউনিভার্সিটি থেকে গ্রাজুয়েশন এবং পোস্ট গ্রাজুয়েশন কমপ্লিট করেছেন। আমরা ওয়েলকাম করবো ম্যামকে, কিন্তু তার আগে জানিয়ে রাখি যারা আমাদেরকে প্রশ্ন করতে পারেন কমেন্টের মাধ্যমে। আমরা পরবর্তী সময় কিউ অ্যান্ড এই পোর্শনে আমরা আপনাদের প্রশ্ন নিয়ে আলোচনা করব আমাদের সম্মানিত অতিথির সাথে। ম্যাম।
Oh, you're waiting for me? Sorry. Assalamu alaikum to everyone. And I'm very sorry that we are late. কিছু টেকনিক্যাল প্রবলেমের জন্য আমাদের একটু লেট হয়ে গেছে. So I hope it is not too late for you. So let's go to the sun right now and see, find out about our own star, which is the sun. All right. So Murtaza, I need to see the presentation.
ওকে ম্যাম, আমরা শেয়ার করছি প্রেজেন্টেশন।
Okay. So ও শেয়ার করতে হলে তার আগে আমি কিছু কথা বলি. So what we'll do, we'll find out about the sun, sun what is its life and what it can happen and how we can study the sun. And to study the sun, we have to go to the underlying science, and an underlying science is the like atomic level, like atomic process, কিভাবে ওখানে ফোটন তৈরি হচ্ছে বা ফোটন অ্যাবজর্পশন হচ্ছে, যেটা দিয়ে we study the sun. Okay. So my presentation, should I মুর্তজা, ওকে সাগরকে বলো আমার এটা শেয়ার করতে।
ম্যাম একটু ডিসকানেক্টেড আমরা কি এমনিতে আমরা কি সাগরের মধ্যে একটু ডিসকানেক্টেড হয়ে গেছে পুরোপুরি। সেক্ষেত্রে আমরা কিছু সাধারণ আলোচনা করতে পারি কি কোনো স্ক্রিন?
No, yeah, I can say it, but কিন্তু না দেখলে তো বুঝতে পারবে না। Okay, let me see whether
convenience actually.
আমার মনে হচ্ছে মানে হোমটা ইট ওয়াজ ওকে, সাউন্ডের জন্য চলে আসলাম এখানে, বাট স্টিল দেয়ার সাম ইস্যু। Let me try again. Why it is not letting me see it? তোমরা জুম ইউজ করো?
হ্যাঁ, জুমে আমরা অলরেডি একটা ওয়েবিনার করছি নাসার একজন সায়েন্টিস্টের সাথে, ওনার সাথে গ্যারি হান্টের সাথে করছিলাম।
Zoom could have been better, easy to.
হ্যাঁ, হতে পারে, বাট সেক্ষেত্রে আমাদের হয়তো বা রিশিডিউল করতে হবে।
Yeah.
কিন্তু জুমে হচ্ছে একটু প্রবলেম হচ্ছে, আমাদের ফেসবুকে আসাটা একটু ঝামেলার আর কি। আমি একটু কানেক্ট করার চেষ্টা করি ম্যাম, কিন্তু তার আগে একটু ছোট প্রশ্ন আমরা এটা নিয়ে আলোচনা করতে পারি যে ওম্যাথ ইনস্টিটিউট সায়েন্স, টেকনোলজি, ইঞ্জিনিয়ারিং, ম্যাথমেটিক্স এর দিকে এগিয়ে আসতেন, তো এই বিষয়টা নিয়ে যদি
sorry, আমাকে বলো। All right, so I can say something about the sun. Okay, just বলতে চাই, and that sun no is one typical star in our own galaxy, Milky Way. And even so, not only it is important that it gives us the energy, it is the energy source for us. Without sun we cannot survive, right? The solar energy, we cannot survive. We have seasons, we have beautiful earth, but we need the sun. So we need to study not only it is our sun, it is also the standard to study other stars in the galaxy. Okay, so like our galaxy, Milky Way, has about 100 to 200 billion stars. And most of the stars, like about 98% of the stars, will follow something like which sun is following, or kibabe birth, kibabe it will keep on giving, energy and ultimately death. Okay, so everything is similar. So that means if we can understand the sun, then we can understand other stars. So whatever the astronomers do, whenever they study any star and try to analyze, they use the data what we know from the sun in that model, and then we give prediction. So that's why sun is very important for us to study. So it has like 9, at this time we have 8 planets. We used to have 9 planets, but Pluto became dwarf, because there are other planets, we don't say planets dwarf like that, around it, so it's small. So if we want to include Pluto, then we have to include a lot of them, and then we will have many planets. So 8 is good enough for us. So ultimately we have to find an exoplanet. Do you know what is exoplanet? Exoplanet means planet which is not, doesn't belong to the sun. So some other star in our galaxy can have planets. There are many exoplanets that we have discovered, thousands actually. So someday we may have to travel there and stay there, but it is still is far away in terms of technology. All right, I can see my talk. Thank you. So let's start from my talk, and I'd like to thank everyone for staying late for this presentation. Thank you very much. Okay, so let's move on. Next slide, please. Okay, so the sun is an object outside the earth. So if you want to study something outside the earth, how do we study, right? We cannot bring the sun into our laboratory and study it. There's one way that we study any object outside the earth, through the light it is giving out. So if we can capture the light and we analyze the light, and then you can get the information of the object. So this is an example how to capture the universe through light. So this particular picture shows an image. It took about 30 years to form this universe. Not yet. You can keep that same page. Yes. Please stay with it. এখানেই থাকো. Okay. So you can see the universe, and in this universe right now we have 43,000 galaxies, not star. Galaxies are put together to form this picture of the universe. So you see different color dot means each galaxy has information added to it. ওই গ্যালাক্সি আমাদের থেকে কত দূরে, কত তার ব্রাইটনেস, কোন স্পিডে যাচ্ছে, all together information দিয়ে এই পিকচারটা we just got this image of the universe, so that's why different colors. Okay, but right now we know we have over 2 trillions of galaxies in the universe. Next slide, please. All right, so this is one example of a galaxy. Galaxy usually has spiral form. It is round, so spiral form, but there are also different other structure, depend how they are forming. So this is a particular one. I put this one because it is an exceptional one, because you can see around the galaxy there are dust accumulation. In general, we don't see so much dust accumulation around the galaxy because they are all sucked in, inside the galaxy. So our own galaxy, which is Milky Way, you can see at night, is also a spiral galaxy. Next slide, please. All right, this is our Milky Way that we can see from our Earth. So this picture was taken by someone. You can see Milky Way, and in that Milky Way, that's the center when you see the broad line going in, and sun exists near the edge of the Milky Way. Okay, it is not toward the center, in the edge, but I like it. There is a reason for it why I like it, because lately there have been many black holes which have been discovered in our own galaxy. Inside there's a monster black hole, and they suck up stars just like that in seconds. So it is safe to be away from the black hole, right? So we are toward the edge of our galaxy. All right, so okay, I just like to say why we study the sun, because about 98% of the stars will lead the life evolution similar to our sun, our star. Next slide, please. Okay, so our sun has 9 or 8 planets, as I mentioned, and you can see the third one is our Earth, where we live and we travel with the sun. Okay, the sun, what is the sun? Sun is a very dense and hot ball of plasmas, intense, very, and it gives out huge amount of radiation. Okay, but you can tell, the size of the Earth is very small compared to the sun, because the radius or the diameter of the sun is 100 times bigger than our Earth. So we just get a very small fraction of the radiation coming out of the sun. Next slide, please. All right, and because of that radiation, we can survive. We have enough energy source for us to live on, to grow plants, and feel good and live safely. And because also our Earth is a little bit tilted, also it gives us seasons, so we can have different kind of beauties around the year. Okay, so sun, so that is why we need to study the sun, because it has a lifetime. Even though it is continuing, but it has a lifetime. And it is also, as I mentioned earlier, is the standard to study other stars in the galaxy. Next slide, please. All right, so we have been studying space and the astronomical objects for a very, very long time. But the first observatory was that observatory in Samarkand. It was built by a Sultan Ulugh Beg. So in Samarkand, what he did, he was very much interested in the space and sky. So he built up a madrasa, and behind it, he built up the observatory. And in a high place, and he himself actually found new astronomical objects, and he put them in the record. But he was very much obsessed with the study of astronomy, so people thought he had gone crazy. So as I read, I don't know how true it is, but that's what I read. So he was probably thrown out of the window of his observatory one night because he died outside, like thrown out from the window on the ground, because people start to talk about him that he has gone mad or crazy. All right, but it's a recent BBC article tells that even before his first observatory in Samarkand, there was one not as advanced that he built. There was another one in Iran, in Persia, and it says that he got the idea to build the observatory from that Persian observatory. Next slide, please. Now we have many observatories. We have two kinds of observatories, like telescopes. When it is in the space, often we call it observatory, and when it is on the Earth, we call it telescope. So why we have a telescope on the Earth, also up in the space? The reason is, again, something you have to go to the atomic level. Okay, reason is that our atmosphere. So our atmosphere has molecules and atoms. So whenever the light is coming through our atmosphere, part of the wavelengths get blocked by atmosphere. This blocking, because the atmosphere absorbs the energy, that's how it is blocked for the light to reach the surface of the Earth. So we can put the telescope and capture those photons coming and study them. So, and in this plot, if you look, I don't have the pointer to show. So if you look at the lower plot where you can see like kind of gold in a line, this line is this covering, it is called opacity. Opacity means like opaque. Opaque means light cannot go through it, right? We know transparent, translucent, and also opaque. So opacity gives measure of opaqueness. Okay, so if it is opacity is high, that means it is more opaque. That means light cannot pass through. So you can see that atmosphere in the lower side is, draw a line. That means, and the wavelength goes from infrared region to, extreme, like X-ray to the larger wavelength, like radio waves. So when then very small wavelength X-ray, they try to reach the surface, the atmosphere absorbs it. So because the opacity for X-ray is very high. But then when you reach to the visible region, then opacity is low. So those photons, which we can see, those photons can reach the Earth, and we can put a telescope right on the Earth to capture those photons and study the object. Again, if you go to infrared region, partial photons, part of the photons can come in, part of the photons cannot come in because of the high opacity. And so in that case, if we want to study that object, which is giving out infrared radiation, then we have to put the telescope up in the space. If the radiation comes down on the Earth's surface, then we can put the telescope on the Earth. So that's why we have various kinds of telescope up in the space, because those telescopes can capture the photons which are not able to reach the surface of the Earth. So radio waves can reach the surface of the Earth. So we have like a radio telescope on the right here, you can see here. All right. So now you know the word opacity. Remember, I'm going to use the word later again. So opacity means measure of opaqueness or measure of radiation absorption by the material. so that the light cannot pass through, or part of the light can pass through. Opacity low, that means part of the light or photons can pass through. Next slide, please. Okay, so these are the examples of the telescopes we have on the Earth and in space. So one on the top, this is an LBT, Large Binocular Telescope. You can see there are telescope, and Ohio State University was one of the 4 entities which built this telescope. Took more than 30 years. Okay, and there are 2 mirrors. Each one is 8.4 meters, so it's huge mirror. So it can overall it can collect the telescope lot of photons to study objects, and this is in Arizona. So this is the Earth-based telescope. But in space we have many telescopes which we call observatories. The one because for the sun is called SOHO. Okay, this SOHO is right here on the left side. This is the SOHO telescope to study largely for the sun. So this is not the only one. There are many other telescopes which are focused to study the sun. And on the right side, you can see the space station. So we have various ways to study the space. Okay. All right. Next slide. All right. So now we can study now how our sun was born. Okay. All stars like our sun, they are born, they go through a lifetime, then they die. So they have a life cycle. Okay. So what happened, even though space is largely empty, but there are electrons, atoms and molecules, they all travel. And whenever they travel, due to gravity, slowly they come together and they accumulate, due to gravity, and they form something called gaseous nebula. So when they form, then due to gravity, part of the gas where you have large accumulation, they collapse due to gravity, and then start to form star. And when they form star, then it starts to shine. Okay, why it shines, I will tell you later, next slide. But usually I can say that of those stars to form, and usually because there are a lot of dust, so you just don't get one star. We get a bunch of stars, they keep on forming. They may take different time, but they start to form around the same time. So there are quite a number of stars they form in that cloud, the dust or cloud. But so here, okay, so it takes at least a million years to form the star, because everything is a slow process. They have to come to gravity, then they collapse, they start to form, the inside the collapse in a star, you have to ignite the nuclear fusion, then the light will start to come out. Okay, but this particular image I put intentionally to show that this is a popular image. So whenever you see this image, you will remember, oh, I see this image. This is the birthplace of stars. So this is called nursery of stars. This particular gas cloud is called in Eagle Nebula, and you can see the cloud like a pillar. So they are called pillars of creation. So, and you can see that stars have formed, and there will be more stars they are forming. So this picture is particularly for you to remember because it's common. This picture is quite popular. But there are many places like that, the dust cloud, where stars are being formed. Next slide, please. All right. So, for example, our sun has been formed. So, sun is a typical star. So I'm just showing the sun just to show how stars start giving out light. So you can see in this there are 3 regions. Okay, and the star, like it's a section. It is showing a section of the sun, and you can see at the center it is called core. Okay, so this is the region 1, and outside the core is called radiative zone. Still here, plasma is very dense. Tightly compact, but outside layer is called the convection zone. where plasma is traveling, moving, they are like boiling, this convection zone. So there are three zones inside a star, or you can say our sun: core, radiative zone, and the convection zone. So in the core is so dense. At this time, our core, this sun's core, has like 100 gram per cc. So it is so dense that it's more dense than anything you have seen in your life. It's very dense, and the temperature is 15 million Kelvin. So it is very hot and dense. That means it is the perfect place for nuclear fusion. So most of the elements in the universe is hydrogen, right? So we know, so what will happen? Two hydrogen, when you go there, nuclear fusion, they fuse. Two hydrogen will fuse to form, next one is what? It is called helium. So when they form, part of the energy will convert. When they form, it will, the total mass will not be equal to 2 times 2 hydrogen atoms. It will be like, a little bit less. That little bit less amount of mass actually converts to energy. And at this nuclear fusion, the energy comes out as a gamma ray, very energetic energy, light or photons. So these gamma rays, they will come out and travel through this radiative zone, still very thick plasma. Plasma, usually hydrogen, it has also other elements. So this radiation will be, absorbed, because whenever there light that atoms and ions can absorb for excitation, they will absorb the photon. So they will absorb the photon, but they cannot hold the photons inside, because there is a lifetime for excitation. So it will give out the photon. So sometimes it can give out the whole photon energy, or it will give you part of the photon energy. Okay, so it depends on what it is coming out. So that photon and also a part of the photon may be used, to give some kinetic energy to the atom. So as the photon is absorbed, when it is coming out, it will be less energy than being absorbed. Okay, what it had before absorption. So that those photons will travel through the radiative zone, then through the convection zone. But each time they are traveling, they will be absorbed and emitted, absorbed and emitted. So the photon will start losing energy that is traveling through. Finally, it will reach to the surface of the sun and escape the sun. So then it will travel in the space. But by the time the photon, which started as gamma ray or gamma photon, by the time it has come out, it has lost so much energy that it will be like an optical photon. That means visible photon, which we usually can see. So this is this kind of process where a photon is losing energy by the material is called the opacity. So the photon, we see, the radiation coming out of the sun has gone through an opacity out inside the sun already. And because of this opacity, the traveling has been slowed down. So the photon created at the center has taken long time, because it gets absorbed and emitted, so it slows down. So the opacity is also causing the photon to slow down. By the time it reaches here, it has probably taken 1 million years. Okay, the photon created at the center may take 1 million years to escape the sun and travel in the space. So these are the photons, okay, we see outside, and that's how the sun starts to shine. Okay, that means all these atoms or in the sun, they are absorbing the photon and emitting the photon. So they are getting excited. All the atoms get excited and de-excited. That process is giving out the light from the star. So that's where all the stars, twinkle, and we see, light coming out. And from capturing those photons or the light, we can say a lot of information about the star, or any other astronomical object, like nebula, where nebula means like gaseous dust together. It is not just a star. All right. So I'm going to talk something about this boundary. When you go to from core, it is radiative zone and then convection zone, and there's a well-defined boundary. See, radiative zone where the plasma is very dense. It's not much motion, of course, motion, but it is dense. But outside in the convection, the plasma is like a boiling, going through a lot of motion. So there are two kinds of phases, and there's a boundary between them. It is called the boundary between convection and radiative zone, and a lot of study is concentrated at this boundary zone, including us. Like our group at Ohio State, we belong to also big group. We study this zone very much. There's a reason for it, because this boundary is known where it lies. This boundary, it is the sun also oscillates like this vibration. So from that vibration, it can we can determine where this boundary is. So it is known very accurately. So if we do atomic physics, we study the atoms, how energy is being absorbed and emitted. With those information, we can actually predict where this boundary should lie. So if our atomic calculations are accurate, then prediction should match with the observation. But at this time, they are not matching. So it has been a long-standing problem to solve. And I've been working on it for many years, and it is not solved yet, but it seems like we are going toward some point that we'll be able to solve it. So at least the discrepancy will be reduced. So there'll be smaller discrepancy. Hopefully we'll be able to solve it. All right. So that means that we have to study the opacity. Opacity, is the quantity which will be used to measure, calculate the boundary. And opacity, this word is always used in model because opacity is used in astronomical models or astrophysical models. So it is very important to calculate the opacity of the radiation. So that means opacity of the plasma, we say that when the radiation is passing through this region, how they are being absorbed. Okay, all the photons are being absorbed, giving a measure of the opacity. So this is a very important quantity, but also very complex to calculate because it involves a lot of processes. So we have to add all those processes to get the final opacity of the plasma. Next slide, please. All right. So now this shows the periodic table. How we know when Big Bang we had hydrogen. So how do we get all these elements? See, all these elements you can see in the periodic table. It starts from hydrogen. You are not able to see my cursor, but I'm using my cursor. The first hydrogen going. See, we have 118 elements listed in this periodic table. Okay, so these elements are formed inside the sun. Not all of them. So when there's nuclear fusion, so hydrogen, fusion will give us helium, then more fusion, lithium, they will go on. Okay. So as the time passes, the core of the sun will become, hotter and denser. The hotter and denser it will become, the more fusion, like heavier elements will start to form. Okay, probably going up to carbon, nitrogen, oxygen, like that. The final product usually inside this nuclear fusion is the iron, because it stops. You can see iron is on this, on the row, one of the top rows, right, the complete row, the white, the iron has 26 electrons, or atomic number is 26. So, and it also has the strongest nuclear force, and that's why where the fusion stops. And then it can go up to nickel, but usually that's where it stops, inside the star. But what happens, all these elements, they do form inside the star, but in a process is called S process or slow process. Okay, that means slowly one neutron will add to another atom and there'll be beta decay and then add another proton. So it takes long time, slow process. Some of these elements will form inside the star, but they form largely during supernova explosion, not inside the star. So when is a large star goes through an explosion, supernova explosion, that's the time sudden compression and forms these bigger elements. So we can see in this periodic table we have these white ones which are solids, and you can have gaseous. The pink ones are gaseous and the blue ones are in liquid form in nature. But you can see also yellow elements. Those are like artificially produced elements. These elements have been produced in the laboratories, but we knew they existed. Okay, they are supposed to exist, but then we tried in the laboratory whether this kind of element actually form or not. We found that yes, they do form. So that's why they're yellow. But now what we are finding, all these yellows should slowly go away. The reason is that we may not find it on the Earth, but we have found that these elements, one by one, we're seeing more and more elements exist in some other star. That means that element form naturally in that star. So that means we don't have to do artificial. They actually exist naturally. Okay. So this and Earth, but we should be lucky. One thing that our Earth has lot of these elements, even though typical star forms hydrogen up to going up to carbon, nitrogen, oxygen, maximum probably iron, nickel, but we see like gold, platinum, silver, which we like very much, and also other lanthanides, all these heavy elements we see because our sun, when the sun was forming, it has lot of debris of remnants, supernova explosion, scattered lot of heavy elements in space. So our sun, when it was forming, they already all were there, all these heavy elements. So they came with the sun and to our Earth. So that's why we have so many elements, okay, on our Earth. Okay, so before I move, I'd like to say one thing about these heavy elements. We know they form by slow process inside a star, but they form in a rapid process called R process when supernova explosion happens. There's another way. This is the most recent understanding that we can form these heavy elements also through merger of two black holes or neutron stars. Next slide, please. All right. So this one shows the abundances, how much of each element we have in the universe, for example. So you can see on the left, on the top, it starts with hydrogen. So hydrogen is the maximum amount, right? After that, we have helium. Then next, we can have carbon, nitrogen, oxygen. Then abundance goes down. Okay, suddenly there is a peak, iron. Then iron is more abundant compared to many other elements. And then peak goes down. On the right side, it continues, but it goes down so much, so it's a different scale. But all kinds of elements are available, exist, and different places. Now the right side shows different astronomical objects where we can see a lot of heavy elements. Okay, so we can, so I like to say something about this. Yes, so I'd like to say that, even though hydrogen and helium are the main ingredients, because hydrogen is about 90% of the all matter in the universe, and helium is about 7%. Okay, so remaining all those elements are they compose the 3% of the matter we know. Even though it is the 3%, but these are the ones which give us maximum information when you want to study some astronomical object. All right. And also I like to say that, the matter we see, even though our Earth is hard rock, we live, but not all the planets, after Mars, the planets are gaseous, right? Saturn, Neptune, Jupiter, they are all gaseous planets. They are not solid. We cannot live there. They're gaseous. So if you want to live, some planet outside the Earth, we have to find a place which is rocky surface so we can walk, or it has to be a little bit far away from the stars so we don't get burned by the solar or the stellar radiation. Okay, so but I like to say that 99% of the matter that exists in the universe, they are in the form of plasma. So we have 1% of the matter, they are in a solid form. Okay, next slide, please. All right. So I just like to say something about the elements of life. See, we see many elements scattered in the space, like hydrogen. They form and they are scattered in space. Hydrogen, nitrogen, phosphorus, or calcium, potassium. We see this, and something. Our body is made from that. That's why it says that we are made of stardust. Yes. So this is one thing, naturally this is iron. This iron, we don't have natural iron on the surface of the Earth because it's not pure. It mixes with something if it is available, iron oxide or something. But pure form comes only from the space. So if we detect some iron or pure iron on the surface of the Earth, that means it came from outside. It was not from the Earth. Okay, but iron is very important. It is also in the blood. We have this red blood corpuscles, and it has iron inside. That's why it is red. Okay, so we have a hemoglobin, the iron in making it red. So iron is, so all these elements form our life. Okay, and I just say this picture was created by Ohio State University because it leads something called all scan SDSS, like a sky digital sky survey, SDSS, small digital sky survey, I think, SDSS. So they detected the elements and they showed these elements exist in the various parts of the body. So it will say how many percent hydrogen here, oxygen, where is the oxygen? Oxygen, we know lung has a lot of oxygen. So this is a beautiful picture, and I thought I'll show it to you. Next slide, please. All right, now let's talk about, because sun is important, what kind of life it will have. So this picture shows the life of two kinds of stars. One is standard or average mass, and the other one is heavy mass, massive star. So our sun is average mass star. So it starts on the left side, so the dust cloud. So this is the average star, like our sun, or it can be a massive star with a lot of materials. So ultimately, what will happen? All the hydrogen in the star, they will fuse together to form heavier elements, and at some point, all this hydrogen will burn out. So we'll not have any more fuel for radiation coming out. So what will happen? The core will become very hot, strong, and all this matter, they will expand, because of the radiation around it. So there'll be expansion of materials. It will become a red giant. The sun will turn into a red giant after all the hydrogen, have been used up or burned. And if it is a heavy, massive star, it will become not really red giant. We call it super red giant. And then it will be different. The red giant, what will happen? The temperature in the core keep on pushing the gas outside, and it will form planetary nebulae. This is the name given, planetary nebulae. Okay, so there will be core inside and gaseous layer outside, illuminated by the heat or the radiation coming out from this core. Okay, and this will slowly lose all this gas, because they will be repelled by the radiation. So then it will all go away, and it will ultimately become a white dwarf. So this core will just keep on shining and shining for a long, very, very long time, until all radiation will go out and it will become a black dwarf. But we haven't detected any black dwarf yet. But that is the idea. What will happen when all the energy will go out and it become cold, so it will become black dwarf. But what will happen to the massive star? Okay, so when it is so big, supernova, then there will be collapse. What will happen? Due to gravity, they will all go in to collapse, all the matter. When they collapse, then there are a lot of electrons too, right? And negative charge. So there will be repulsion too. Then it will explode. Okay, so that is what supernova explosion. Okay, so it will explode, and during this heavy compression and explosion, all these heavy elements, heavier than iron, they not only iron, even before iron, all kinds of elements will form and scatter in the space. Okay, and then and the core, if this core scattered, even the core is very big, then there's two choices. One is will become either a neutron star or a black hole. Neutron star, when the core is heavy, but it is not, gravity is not very strong enough to compress to a singular point, then it is a neutron star. Just before formation, a stage before formation of a black hole. But if the gravity is very strong and then compressed, then it will form a black hole. So these are the life, ultimate life, starting from gas cloud, heavy massive star will become either a neutron star or black hole, and typical stars will become like a white dwarf. But one thing is that 98% of all stars are like standard average star, and they will become white dwarf. Only a small fraction will go through this massive process and supernova explosion and black holes. So then the formation of black hole is, say, very less than 1%, maybe 0.0, that's what it says, 0.07%. Even with that, with when you have billions of stars in the galaxy, that means there are a lot of black holes too. Okay, next slide. All right, so let's study our sun. So what will happen to our sun when it becomes a red giant? So this is the comparison. So our sun is in the middle of its lifetime. It has, at this time, its current age is 4.5 billion years. So it is going nicely, smoothly at this time, but after 5-6 billion years, it will become a red giant star like that. So the current size will become huge like this on the right side. That means it will cover the whole earth. Everything will go inside because it will become so big. So that means, we have to find another home. When it becomes red giant stage, we need to find some place to go so human race can continue living in the universe. And our universe is right now is 13.8 billion years old. So that sun formed way after the universe started. All right. Okay, so next slide, please. So after red giant, then it is the example of planetary nebulae. So I talked about planetary nebulae. Red giant will keep on pushing out its gas by radiation and heat, and ultimately form a red giant, planetary nebula. So this is an example. There are all kinds of planetary nebula, beautiful ones. But this particular one I choose to show because you will see this very often. So you can immediately recognize that, oh, I know this one. This is the Planetary Nebula. It is the death of a star, you can say. So at the center, this core is very hot, and we have this blue gas outside and the red gas outside. So this blue, is largely oxygen, and the red, that's due to nitrogen. So I tell a story about my doctor. I've said that a number of times in my talk. So he told me he is a doctor, but he likes physics very much, and he likes astronomy. So whenever I see him, he tells me, "What's new, Sultana?" So he told me once that, "Sultana, I have a rabbi friend." Rabbi is like, we have imam. The Jewish people have rabbi. He made friend with this rabbi in Israel. So from Israel, this rabbi told him that, we have found the eye of the God, and God is very angry because you are not doing things properly. So then he asked me, do you know about this eye? I said, no. So then I asked him, why don't you email that eye so I can find out? So he emailed me this picture. So then I told him, it is not eye, it's just the death. It's just like a dead star, a typical star which died. Okay, so but it looks like an eye. All right, next slide, please. All right, what will happen? So all are dead. So the gas after that will become white dwarf. But white dwarf is still so compressed and hot that, the lot of carbon is inside. They started to convert to diamond. Okay, so this is particular one came in the news, and I thought, I will show this one to people who will be interested to see that this white dwarf has become just a chunk of diamond in the space. Okay, so the title of this, it is in the BBC News. It says, astronomers discover Earth-sized diamond encrusted with white dwarf. So that means, in 2014. So it is so old. Slowly, the carbon inside has become diamond. It has crystallized to diamond. So if you go to space, someday we'll be traveling in space, right? When the technology will be developed, you are in a place, Jasher University of Science and Technology, you'll be developing a lot of technologies, right? So we'll be traveling in space, and we may hunt for, this kind of diamonds, and just collect the diamonds for business or for use, or even for commercial use. Diamonds are used, right? So you can see the space is rich in diamond. And we know that most of the stars turn into white dwarf, and white dwarfs has a lot of diamonds. Okay, now next slide, please. Okay, so this is our star at this time. Okay, even though from far we say, as Ali Murtaza was introducing you, we write poetry about the sun, the beauty of the sun. But close-up looks is different. It is very hot, very dense, and you can see, it is very tiny, small size of the actual sun, and you can see, the reddish and how hot it is. On the surface of the sun, it is 5,700 degree Kelvin, and you can see, some material on the side. That means it is ejecting out materials. Those are called solar flares. So this ejection on the surrounding, and you can see the white spots. These are like magnetic spots, solar spot. What? Because it is plasma. Plasma means what? The charged particles, they are all together. And when charged particles move, what will happen? It will create electricity, magnetic field, right? So the magnetic field, so slowly these magnetic fields accumulate, and they form these solar spots. And slowly, these spots can increase. And on the average, in every 11 years, there'll be a lot of spots accumulated, and there'll be storm and a solar storm going, and a lot of ejection of materials going out. Is something you like? Am I going too slow? All right. So
No,
this.
it's okay, ma'am.
All right. Okay. So so every 11. So not only that, sun has pole, we call North Pole and South Pole, but because of this turbulence and ejection and storm during this time, when you have a lot of this solar spots, even the pole changes. Okay. Next slide, please. So what happens when there is ejection of material? On the left side, you can see the sun, and on the right side, you see the tiny Earth. Okay, so during the solar storm, lot of ejection. They will reach this. Not only Earth will go beyond the Earth, but we have protection. Earth has 3 protection. Number 1 protection, you see it every time, or you know it. It's the atmosphere, which protects us from anything coming to the surface of the Earth. It burns out small pieces or radiation, blocks radiation. Then outside we have what? Ozone layer. Ozone layer also blocks a very energetic radiation, X-rays, right? So they don't reach. Otherwise, people will have cancer. It can cause cancer, too much radiation coming in. So our second protection. The third protection is the magnetic field in our Earth. You can see the lines around the Earth. These are like magnetic field lines. So whenever charged particles from the sun, they come toward the Earth. So this magnetic field capture those particles. So they capture, they burn, and they remain there and protect us from so protect us so that we are not exposed to these charged particles. All right, next slide. Next slide, please. All right, so what will happen, if the charged particles get captured by this magnetic field? These are real pictures. Okay, the top one shows the Earth, and you can see the huge color around it. Those are, and the round ones, those are like magnetic field. It has captured so much materials. So in 2003, there was a big solar storm. And so a lot of materials came to reach Earth. And then magnetic field captured those, charged particles. And you can see, they model it and found so much material was captured. So they did not reach the surface, but they are captured. So, the image show the amount of radiation coming toward the Earth, but we are protected. But some actually reach, like the Earth. You can see, sometimes we can see this, it's called Aurora. Okay, when they come, they get burnt in the atmosphere, we can see Aurora. So this is one of the picture. You can see all these materials getting burned in the atmosphere. They are not reaching us. So that because the atmosphere is protecting us, but burning looks beautiful. Next slide. Okay, now let's see what happens in the storm. Okay, how do we study a storm? So in this picture, the top one shows the sun and lot of solar spots, the white spots, a lot of those. So when this is happening, we know that the solar storm is coming. And the right below it in the blue, curve, blue picture, it shows, the sun is blocked by the cap of SOHO. The telescope I mentioned for the sun, SOHO has captured, the sun, blocking the whole sun. But the sides, around the sides, you can see how much materials are being ejected out from the sun, right? It is a lot more than the sun, size of the sun coming out. Just show the huge amount. And then go to the almost right corner. You can see this was detected by SOHO. After 8 hours, all the particles came and fell. On the right side, you can see it's called proton shower. So they came and swamped the screen of SOHO telescope. So you can see that, all covered, they came and covered that, this spectrometer cover, okay, cover that lens, or you can say whatever glass with protons. So you can see how much materials coming. After 8 hours, it took 8 hours to travel from there to the SOHO telescope. And on the top you can see two figures. One is showing, it says calcium, iron, nickel. So these are the X-ray radiation they detected. Okay, so there is India has a satellite, it's called SOX. So it detected X-ray radiation coming out, and it is bump into like calcium, nitrogen, and nickel. You can see bump there, and same thing you can see on the right side showing the peaks. So at these energies there are more radiation coming in. Why at this energy X-ray is higher? That is what you can predict by studying the atomic structures like iron. So why? And because the iron can show that this kind of X-ray radiation can peak, or calcium can show that, nickel can show that. So now if we study iron, for example, I'll show an example where this X-ray peak is coming. It will be in the next slide. Next slide, please. Okay, so this is the calculated X-ray peak. You don't have to understand, just look at the top panel of the figure. The top panel shows peaks where this and the energies are in X-ray energy. If you see the peak, all these peaks actually shows the range where we expect to see the energies coming out from the sun, because sun has calcium, sun has iron, nickel, and during that solar storm they were giving out a lot of X-ray radiation coming out from those elements. And this is a proof at what energy we should see the peak. This figure actually predicts that, explains that. Next slide, please. All right. So with all this understanding, now I will go to atomic physics. Before I do that, so there I'd like to say something about called Opacity Project and the Iron Project. Okay, they started long ago, maybe before you were born. So in the late or early 80s it started. So what astronomers were trying to model, like other stars, and they found a lot of discrepancy when they model and predict this kind of thing happen, or we should have that many oxygen atom, but in the observation it shows a different kind of amount of oxygen. So there's a big difference, discrepancy. So they asked, can you study atoms? And so there was a plea, that whatever atomic physics we put in our model, it does not give us what we observe. So that means something is missing. That means there are more elements in the astronomical objects than we know. That's why there should be more opacity, and more opacity causing a big difference between the observation and theoretical prediction. Okay, so when it's said, then someone named Mike Seaton is a big scientist at University College London. He called his students to actually make a big team to work on atomic physics, get the accurate atomic data, study, and put them in the astrophysical models and see whether we can reduce the discrepancy between the observation and the prediction, so that they can explain the object. So in that they started. So I joined later. So I became a member of that project. And this project went for a long time, and it ended in 2007, but it did not quite end in 2007, because then we found some more discrepancies are, they're just popping up here and there. That means we need some more accuracy. So the work is still going on. I'm still involved in it and working on it. All right. So next slide, please. So this shows the two projects you should know. One is called the Opacity Project. So Opacity Project means, try to calculate the opacity, the amount of radiation absorbed by the constituent elements inside the star. And next one was another project started, is called the Iron Project, because iron is abundant in many astronomical objects, but astronomers could not model it because there are not accurate atomic data available. Iron is difficult to study because it has many electrons and properties, so there is complexity about atomic calculations and computations. So, but under this project, we have done a lot of advanced study, and there are a lot of data available on iron itself. As a single person, I did probably maximum study, so that's why a lot of astronomers call me the Iron Lady. Anyway, now we can see that people involved in these two projects, like people, of course, the US, but and UK, because Mike Seaton is from UK. There are France, Germany, Venezuela, Canada, and Belgium. Okay, so there are many members coming from these countries. They form this team to calculate actually to study the atomic processes in the plasmas, in the stellar plasmas, calculate them and put them in the model so that the model give accurate information. Okay, and you can say that it started and ended, well, 2006 and 7. The professor died, in 2008, I think, or 2007. Anyway, we studied all atoms from hydrogen to iron under this project. And then under the Iron Project, we study largely the heavier elements, and we produce a lot of atomic data. And there's so much atomic data that they are in the databases. So there are 4 databases at this time. One is called TopBase. It is in France, CDS, and also TIPBase. It has collisional data. It has radiative data, CDS, an OP server, another one at the Ohio Supercomputer Center, and the 4th one is NORAD atomic data, which is operated by the astronomy department. This is the one that I created. Okay, next slide, please. Okay, what is this opacity calculation for the star? Okay, I'm just telling you to expose. Say, for example, in the middle, you can see the plasma opacity. You can see the blue area. So this is the plasma. And the radiation on the left side, the red waves, the photons are passing through this plasma. And when they're coming, this energy, that intensity is lower. The intensity is higher before it's entering because the plasma absorbed part of the energy of the photons, so the intensity is lower when it is coming out. And if you take the ratio on the right side, the transmission is given by the ratio of the incident intensity and the emitted intensity, the ratio, and from that ratio there's a quantity called tau. It's the optical wavelength, and that optical wavelength depends on kappa, density of the plasma, distance of the plasma where they're traveling, and kappa is the constant. This kappa is the opacity. It gives the measure of the radiation will be absorbed when it is passing through the medium. Okay, so this opacity depends on 2 atomic processes, largely 2. So we have to study the atoms that exist in the sun. So these 2 projects, Opacity Project and Iron Project, they always focused on the sun, because sun is very important. As I said, if we can find accurate numbers for the sun, then we can study other stars and get more accurate information. Okay, so I have written down at the bottom of the slide the 2 particular processes that they are responsible for absorbing most of the radiation. One is called photo excitation. That means an electron or atom is excited when the electron absorbs the photon, and it's a photon absorption, that's called photo excitation. And then the other one is not only it excites, it can also leave the ions, which is called ionization. It's called photoionization. So next slide, please. Okay, this one shows the absorption of photon inside the sun. Okay, so these astronomers who complain that your opacity is wrong because we are not able to predict what is being observed in the stellar. So this shows what is wrong with the opacity. Okay, so in the curve, in the lower, it is temperature versus the opacity. Okay, and it's in log scale. When it is log scale, that means each number they go by 10 times. So the lowest curve you can see will be for hydrogen, and actually I'll tell you hydrogen and helium. If we think the star has largely hydrogen and helium, then you will get the lowest curve, which is called curve A. So in curve A has two peaks. One is around over 10,000 degrees, one peak. So that peaks come for photoabsorption by hydrogen. The second peak you can see, comes from the photoabsorption by the helium. Then there's a shoulder going, and then it is going down. So this shows the opacity photon absorption if we think the star has largely hydrogen and helium. But if we keep on putting more elements, saying this, no, there should be a lot more elements like carbon, nitrogen, oxygen, then neon or silicon or calcium. If we keep on adding, and we keep on adding up to iron to the star, then we get the topmost curve, curve number D. Okay, and the curve number D, there is something called Z bump. You can see that. So what will happen if we add more elements? The opacity will increase. If the opacity will increase, that is the problem. Currently, we have low opacity for the stars and for our sun, but if this opacity, actual opacity should be higher. And because all elements are the same, this higher things come because of some missing physics, okay, which I'll talk about later. Okay, so now explain what is this Z bump. Z bump means this bump came, the absorption came because of all elements starting from lithium to everything, maybe up to iron. So when we add lithium, all elements up to iron, there's a bump. And this bump is enhanced when iron was added to it. That means we have a lot of iron in the star, which can get a lot of absorption, and that means that can increase the opacity to solve the problem. Next slide. Okay, now let's see how to study the underlying physics to know what is going on, how this absorption is happening, so that we can study it. So that is what I study. So left side shows an atom picture. Electrons are going around the nucleus. It's a very, very simplified picture of an atom, because we know electrons, they have fixed orbit. They just don't go random. So they will either stay in orbit 1 or orbit 2, but not in between the two. That means it will have one energy in orbit 1, it will have a different energy in orbit 2, or another energy for orbit 3, and so forth. Each orbit has fixed energy. So that's why we call the orbits or the energies are quantized. That means they have been quantized. There's no plus minus, they stay there. So on the right side, if you see, these energy levels, various energy diagram. So what will happen if the electron of the atom absorbs one photon? Somehow it can be excited to the level number 2, but it will not stay there. It has to come down from level 2 to level 1. When it will come down, it will give out the energy in terms of a photon. So that photon will come out, and that's what we detect in the telescope. The electron can be excited, say level number, say 5. Okay, then it can come down to the lowest level, giving out one photon, or it can also be another atom can come down to level number 2. So it will give out different kind of photons. So we can have all kinds of photons coming out after excitation. And if we pass that photons through a spectrometer, we see lines. Okay, right below the energy diagram, you see the lines. These lines form because they correspond to different energy photons in the spectrometer, and that is we call spectrum. When we separate out different energy photons, we call it a spectrum. So this is a spectrum. This particular spectrum actually belongs to carbon. But splitting of the color into its component is called spectroscopy. And it is happening in the nature all the time, like a rainbow. Rainbow splits the color or the light of the sun into its components, all kinds of color. On the left side, there is an example prism you used in the lab. You send a white light, it will split the color. Okay, what about the component? When combine all this color, it become white. But if you pass through the prism, they will split, all these colors. The reason is that when each color will come out at a different angle. That's the characteristics of the color. So when they come at different angles, so then we can separate them out and see the spectrum. Next slide, please. All right, so this is the atomic process. First process that I mentioned, photo excitation. So you can see the two levels, E1 and E2. A photon is entering into the atom, and the electron in E1 is excited to go to E2. Okay, and then it comes down. When it absorbs the photon, it is excited. When it comes down, it gives out the photon. Okay, and that is what showing in the picture on the left. Now, when it is coming down, the photon comes out, and these are the photons that we study, as I mentioned, in the telescope and get a lot of information. These photons are different for different atoms. So when we detect a photon, we look at the energy, and if that energy matches that of the carbon or oxygen or iron, then we say, okay, this photon came from iron. That means iron exists in the star. Okay, so that's how we identify the elements in the star. And if we want to study, we calculate the quantity. We call something called oscillatory strength. Okay, related to the probability of excitation. And on this, there's an equation at the bottom, kappa. Kappa is the opacity. And you can see on the right side, these are all constant. Pi, E squared, MC constant. N is the density of the plasma, electron density. Okay, and F, you can see the F is the probability of that atom will be excited to go from state I to state J. So this is the probability, this is the equation we use. Okay, so this is for the first process. Second process, I will discuss, but let's finish this first process. Next slide, please. Okay, so we said that we see spectrum. When the light is absorbed by an electron, it goes to excited state, and we call it absorption. It also produces a spectrum, a line, no light line. And when it comes down, it gives out photon. That photon has a color, so we can see in the emission spectrum. So two kinds of spectrum we study: absorption spectrum, other one is called emission spectrum. So this spectrum you can see in this picture was taken long ago, like 1815, Fraunhofer, when he was studying the sunlight through the atmosphere. Okay, and then he saw this spectrum. When he was trying to study, he found lines, but that time quantum mechanics has not arrived. So he didn't know how to tell this. He says, what is this line? Well, something in the related to sun, he did not understand. So he denoted them by A, B, C, D, because he did not know what they mean. Okay. So ABCD. But after, you have to wait for 100 years, much later, so there are two people came, Russell and Saunders. Now they explain what these lines are. Okay, so then quantum mechanics came in 1905, and then I started, that all things to study wave function. It kept on improving. 1905 or later, it was Schrödinger started Schrödinger equation. So in 1925, Russell and Saunders explained that, this kind of photon quantum state, one quantum state, another quantum state, you can have absorption line or emission line. And only then we are able to understand what is this A means. A mean is found out to be a line, which is 7594 angstrom unit. It belongs to oxygen. So it is an oxygen line in the atmosphere. Then which he denoted B, it is another oxygen line. What is he denoted as C? That line, 65, 63, it belongs, that is the line coming from hydrogen. And then sodium, so we are able to explain these lines. Next slide, please. All right. So now we can calculate these lines theoretically. So one person lifetime has been dedicated to calculate the lines of the sun solar light. His name is Robert Kurus. He's at Harvard University, and he became well known. He just devoted to calculate all this photo excitation and probabilities, and then make the spectrum and make this. So this is the spectrum that it produced after a long time after studying this. So from the top panel it goes to the bottom panel. Okay, the top panel shows very absorption line, like the lines which will absorb the photon. So it starts with a very low wavelength or short wavelength. As you go all the way, then you come back to purple, next line, and purple becomes blue and a little bit yellowish. Then you come to the next line, greenish, green, it becomes some yellow. Then from yellow that becomes red, and so on. Okay, this is his lifetime work. Well, he's still working. Okay, so and this it shows that the lines, there's so many absorption lines in the short wavelength that when these photons will be coming to the atmosphere is going to absorb all of them. Okay, that's why short wavelength X-ray we usually don't see, directly on Earth. So all of those, block means atmosphere. So he actually did this for atmosphere. Sun coming, so this is the spectrum you can see on the solar radiation passing through the atmosphere. So you can see so many absorption lines that the short wavelength will be absorbed. They will not reach the Earth. But if you come, only place you can see first that at yellow lines, there's not much absorption. That means that the yellow light from the sun is able, the lines are able to reach the surface. That's why the sun looks yellow, because the yellow photons are reaching the Earth. So, so it shows absorption with the other molecules like water and absorbs, etc. But I wanted to show how the spectrum looks like, and this part, that why the sun looks yellow from the Earth. Next slide, please. All right, so now what we did in our study of the sun under the Opacity Project. The left side shows another image of the sun taken by Soho. Okay, this shows, I like this picture because it shows such a hot sun. It's like a awesome. But it has temperature, constant temperature on the surface. So any object, like at constant temperature, they give out radiation. So that radiation can have maximum, wavelength. Like what kind of photons will come out, it depends on the temperature. So at this, the sun's temperature is 5,700 degrees. And at these degrees, the photons which comes out most is given on the right side. Okay. And there's a formula which tells you about this, the photons coming out. So it is called Planck's distribution function. You see the solid curve on the right side is the Planck's distribution function curve at 5,700 degrees. And strangely, you can see that it peaks at a wavelength about 5,000 plus. And this is the wavelength of the yellow color. So that's why, again, the sun looks yellow, because it gives out more yellow photons. And the dots you see in that curve, they are like actual flux, the amount of radiation coming out of the sun. And you see that all these points matching the theoretical curve very well, except two places, at the top and also on the side near low energy region. It's showing that the flux is lower than expected, and near the yellow, flux is higher than expected. Now I'll tell you something from our work. The flux is lower than expected. Why? So this is our study. At the bottommost figure, you can see a lot of lines. This is the opacity lines. That means if the line is high, that means at this energy, the more photon will be absorbed. So that's the opacity. So this is for iron 2. And if you see in this iron 2, you can see the most of the region, where we see high opacity, that means high absorption of radiation, matches exactly with that in the sun in the top figure. So that means on the surface of the sun, flux is reduced by iron. Iron is absorbing the flux, so the flux is not able to go out. So we see lower than expected. So then the question you may ask, why iron is on the surface of the sun? Well, it is on the surface of the sun, even though it is much heavier than hydrogen, it is on the surface of the sun. The reason is that there is a pressure. This pressure is holding iron ions on the surface. It's the radiation pressure. There's so much light, so much radiation, it is pushing the iron ions to go to the surface and balancing the gravity, pulling it down. So that's why the iron is on the surface of the sun, and we can see it. And this iron is absorbing the flux, and that is being proved by our work at the bottom. Next slide, please. Okay, it's the second process that I will talk about. The second process is photoionization. So, okay, you can see atom and photons are traveling, okay? So one of the electron will capture a photon, and on the right side, and the electron will have enough energy to leave the atom. So it has freed itself, it is going to space. So that means we have ionized the atom here. So this is called photoionization, because we have carried out the ionization by absorption of a photon. Okay, this process can be direct. This shows equation here. So this, they say, for example, it is an ion, and the photon is coming, and the photon is being absorbed by an electron, and it is going free. Is epsilon here is the free electron, and you have one more additional positive charge here. But between these two processes, photon being absorbed and electron being ejected, there's another process called intermediate process, autoionizing state forms. So there's a state which is formed in between these two states. This not all the time, but a lot of time it will form, and it forms, and then it breaks down. Okay, it's called doubly excited state. That means the two electrons will be excited and form this state, and then it will break down. But the importance of this intermediate state is that it introduces a resonance in the process, in photoionization. That means, you know, photoionization, and you are ionizing the atom, ionizing at sudden energy, there'll be peak. That means ionization will happen very quickly, a lot more ionization. That is because there is an intermediate state formed at that energy, causing this resonance form. So the relation between the opacity and photoionization cross-section is the, you know, probability of ejection or ionization is given by the cross-section sigma. So it is depends on the cross-section of photoionization. Next, please. And photoionization is happening all the time. So in the sun, the outside the sun is called photosphere. So there are a lot of, you know, ions or electrons around here, and the photons are traveling, and photoionization is happening. Okay, so this is one place we know a lot of photoionization is happening in the corona. It also happens in a nebula where stars are forming, or any nebula. So this one shows a Lambda Centauri nebula. You can see there are a lot of light, you know, stars. That means a lot of stars means a lot of photons. The lot of photons mean they are being used on ionizing. So photoionization also happens a lot in the nebular atmosphere. Okay, so this process not only there, it is happening right in front of you right now, because you are watching the monitor, right? The monitor has also photon coming out. So it is coming out and being ionized, again recombining, because they cannot stay ionized for a long time. The process is happening. Next slide, please. All right. So this figure shows the energies when we can have this resonance, you know, sudden peak or sudden high probability of having photoionization. Okay, look at the purple curve, and you have seen it in the class, I'm pretty sure. You have energy diagram like I showed in earlier. So it's the lowest state, the electron can be excited to this orbit or that orbit and different energies. Ultimately, it can go to a level, see that where E is 0, the energy. When the energy is negative, electron remains bound to the system. When the positive, it becomes free. So this means continuum is called free state. So electron is free. So this is the typical condition. But what will happen, you know, after this, we can say electron is free, so we have ionized. So we have ion here. This ion can also have excited state, one state, another state, third state. These are all excited states. But below each excited state, you can see there are lines. These lines are called, you know, Rydberg states or quasi-bound states. So when the electron energy, a free electron energy, matches this energy and combines with the ion, it forms a state, and that form is the autoionizing state, which breaks down and photoionization happens. So these are just showing when it is happening. It's just the energy diagram to explain the creation of resonance. All right. So I don't know your level of atomic physics that you learn from the class or research, but this is something you will be learning if you study a higher level atomic physics. Next slide, please. Okay, so when you have that, then you can calculate the cross section. We don't have to look at anything except the bottom one. Okay, this is the equation that we use to calculate the cross section, and in that there is a parameter, or you can say notation S. S is the gives the probability of going from state 1 to state 2 due to photon interaction. Okay, that's what it is defined in this slide. All right, next slide, please. And I like to say that, you know, it is not that simple calculation. So to calculate that kind of quantities, I have to use very accurate method, which is called R matrix method, close coupling approximation, that I use, and they take a lot of time to compute things. So I have to use supercomputers at Ohio Supercomputer Center to compute those cross sections. And not only that, before I compute, a lot of physics that have to be involved to set up the mathematical form, like the wave function, how we describe the atom. You have to have good wave function to represent the status, and then you calculate matrix, and you have to take the probability of many excitation where the photon can be absorbed. So it becomes very complex, but it can be done, just needs time. Okay. All right. So this figure, this slide shows the results. Okay, comparison photoionization for photoionization. The top panel shows the experiment done in Germany. There's a setup called BASI-2. So where they measured photoionization cross section, and you can see the lines. These lines, these are the resonances. Okay, photoionization resonances. So for example, photoionization is going, is happening if you start from the left, okay, and then suddenly there is a peak. That means a lot of ionization is happening in this energy region. Again, then it drops down. Again, photoionization is happening, but at a lower level. Then there's a sudden peak. Again, photoionization will happen at a higher rate. So this is what actually they measured in the laboratory. But even before they measured it in 2010, they published it. I did the calculation maybe 12 years ago, or I don't know how many years ago. So, or at least 7-8 years ago. So this data, I told you that I have a database in the astronomy department, NORAD atomic data. And NORAD atomic data has the data for photoionization of nitrogen 4. And if you plot the predicted cross section, the blue curve at the bottom shows how it should look like. And you can see that blue curve matches the top one in the green, or so the green, or sorry, the features. It has a green and green. They put, they somehow they calibrate, but the resonances are given here in magenta or brown colors. So you can notice that how predicted theory match the experiment carried out later on. Okay, so that is how the photoionization cross section looks like, and each resonance means more absorption of photon. That means you increase the opacity. Go to the next one. Okay. Now we come to the solar problem. Okay, so the top panel shows, you see the red curve and the green curve. Okay, those are like showing temperature of the sun and the density of the sun. So you start, 0 means the core of the sun, and 1 means the surface of the sun. So as you go from core to the surface, the temperature decreases, density decreases. As you go, there's a dotted line. And this dotted line is the boundary that I mentioned between the radiative zone and convection zone of the sun. And this zone has been measured, and it is supposed to be 0.713, very accurately measured. But with the current atomic data, if you put into the calculation of opacity, and then try to calculate the depth, optical depth, and this depth comes out not at 0.713 but at 0.726. That means it's very large. That means opacity was not accurate. You may say, what is it? They look so close, but they are not very close for the sun, because sun is huge. This little difference is equivalent to 5,600 miles. That means, if we use the predicted opacity, that means sun border has increased by 5,600 miles. So that is something in a way out of the actual situation. So that means, so that's why the problem is big, and we are trying to calculate, the accurate opacity. Not only that, so people used to think, we know a lot of things about sun, but doesn't mean we know everything very accurately. We say that much amount of carbon we have in the sun, that much amount of oxygen we have in the sun. But later models showed that what we thought, they are less than actually, what we thought. So if it is less number of atoms, but still we want to increase the opacity, what is wrong? Wrong is that there are missing physics in it. Okay, what is this missing physics? I'll show you next the calculation. Next, please. Okay, calculation. So we did our calculation, been doing calculation, but then the laboratory came forward. Sandia National Lab in the US, which is in New Mexico. So they have a setup called Z-pinch setup. So they thought of, okay, we'll measure the opacity of the plasma near that convection boundary. So this setup, this is a picture you can see, it's 40 meter long. So you can tell that 40 meter, it's a big setup. And it can see it's illuminated at this time because the experiment is going on. And there are a lot of cables in them. And the whole thing, purpose of the whole setup is to create very intense electricity, powerful electricity and magnetic field. So right at the center, there's a very small setup. In that setup, they put a very small piece of iron, and there's a gold thread going through it. And then they send 27 million amp current through that gold foil at the center. When the current goes through it, then it just explodes, and that means the plasma is created. So much X-rays are created, and also the iron is there, is vaporized. So then we create a plasma. In that plasma, it will be so much magnetic field that it will compress the whole thing or implode the plasma into a small part, but in that, the density and the temperature will be similar to that inside the sun. We could not do that before 2014. So when it was first time done, create that kind of plasma, very dense and hot plasma, and something you call local thermal equilibrium plasma. It was not created. So we said that we brought the sun on the earth because we created a little plasma which is similar to that inside the sun. And when the radiation goes through it, then they can measure the opacity. So they measured the opacity. And just before I move to what they found, I would just like to mention that, so they had 60 shots, before they wrote the paper. We are also co-author in that paper. It was published in Nature letter. So they, in each shot, cost I think about $220,000, and it used so much power each shot that is more than the whole world. That we are using power, everyone in all countries, the amount of power the whole population in the world using, that shot has more power than we were using. All right, so actually more current. So to go to the next slide, I'll show what they found. So this is, in this, there are 3 panels. Just look at the top panel. We'll talk only the top panel, okay? Because they are all similar. The black curve you see, that is the opacity with respect to wavelength. That means, some certain wavelength they choose, and what will be the absorption in this wavelength range. The black curve is the actual measured opacity, and down below it is the blue curve you can see, right? And this blue curve is what they did. They took our data and calculate the opacity. So blue curve is the calculated opacity, and the black one is the measured opacity. You can see that there's a big difference. That means our numbers, whatever we calculated, available values are way different or not inaccurate to explain the experiment. So this is what we have been working on to resolve this issue, opacity discrepancy, reduce the discrepancy in the opacity so that it can predict amount of elements exist in the sun or any other stars. Okay, so what we thought, or what could be the reason for discrepancy? We can see the peaks, the position of the peaks match. This position of the peaks came from the first process that I mentioned, photoexcitation. But the background, which is lower, the background was obtained from the contribution of photoionization, the second process I mentioned. So we focused on the second process to see whether photoionization gives more opacity than what we have already. Okay, next please. Next slide. Thank you. So this one has 3 panels. Okay, the top one is the same you saw in the last figure, but the color has changed. The red curve on the top panel, red curve is the measured opacity, and the blue ones are the calculated opacities. Okay, now what I did, okay, so calculated the cross section for iron 17. In that hot temperature and density, there are 3 dominating ions exist inside the sun: iron 17, 18, 19. When I said iron 17, it means 16 electrons have been knocked out. That means it's neon-like iron. When it's iron 18, that means 17 electrons had been stripped off from iron. So the iron is so hot, the environment is so hot that electrons have been stripped off from the iron. So if you take out 18 electrons from the iron, that is iron 19. If you take out 17, it is called iron 7. If you take out 17 electrons, it's called iron 18. These are like astronomical way to astronomers use numbers. In physics, we use like plus, like 2 plus means 2 electrons out. In astronomy, they will not say 2 plus, they will say 3, because number 1 is the neutral atom. So what it is, because I know iron 17 exists in that temperature, I just want to, we, our group, and I did my part is to calculate the cross section, and my colleague Anil Pradhan calculated the opacity. Okay, so combined together, the results will be shown to you. So what I found, after we calculate the cross section for photoionization of one ion, iron 17, to see what happened, we found a huge difference. In the second middle panel, see there's a blue line. Blue line is the earlier calculation. Okay, so it's line going smoothly. Okay, no, nothing, and that is grossly underestimated cross section. And you see the red and black curves, those are like first calculation and the second calculation. We are just comparing, and you can see a lot of resonances that I mentioned. Each means resonance means absorption of photons, that is more opacity. So you can see that more accurate calculations show that there should have been more absorption, which was not included when the calculated opacity was now done, or a calculated opacity were obtained. Okay, so you see that the new calculations show that will increase the opacity, and it should match close to the experiment. So this is our new finding, but it involves a lot of work. Because the plasma doesn't have only iron 17, it has 18 and 19. Those also have to be included in the opacity calculation, and also modeling. There are a lot of other things will be included, but the main contributor for opacity, and we found that there's a main contributor which is missing in the earlier calculation, and hopefully this added part will resolve a lot of issues. So we did a sample calculation. after I calculated the cross section, my colleague Professor Pradhan did the opacity, which is in the next slide. All right, the next slide you can see now is the opacity with respect to the photon energy or the wavelength. And in that you can see black curves. There are some dotted black curve. There is one solid black curve. So dotted is the one which the opacity obtained using the earlier calculations, and the black one using the new calculations. If we do that and integrate to the opacity, we increase the opacity by 69% just for one ion, iron 17. So now we know that this has been one source of missing physics, or the source of discrepancy in we had for the study of the sun. All right, so right now we are working on other iron ions, and then Dr. Pradhan also is working on his code to calculate the opacity more with the more accurate modeling, and we hope to resolve the problem. All right, so that is all I wanted to say about the sun. Next slide, please. Okay, so this is the book that Dr. Pradhan and myself have written, Atomic Astrophysics and Spectroscopy. It is a very popular book. It is used not only in our department, in many universities in the USA and all over the world. Okay, and I use this book to give lectures even in Bangladesh. Like 2017 when I went there, I also gave courses at Dhaka University and Rajshahi University, and partially Jahangirnagar University. So this is the book. If you want, you can download it, but it is specialized, but it is certain area that you will understand. Okay, you can download the pirated version in the website for your personal copy. Okay, and this has a lot of findings from our study of atoms, and it bridges between atomic physics and astrophysics. So that's why this book is very popular. Next slide, please. Okay, this is the last one. I just want to say, that Ohio State is very much involved in telescopes also, but not all the universities where astronomy department exist doesn't mean they build telescopes, but some universities do, few universities, and one is Ohio State University is one of them, which builds telescopes. But this is LBT is one of them, but it is also involved with other telescopes. And the lower pictures, these pictures were taken by LBT of the galaxies. So I thought I'll show some nice example. Thank you.
Thank you very much, ma'am. I think that it was nice and fantastic presentation from you. And so you were here and there, and that is why you were 1 hour late. While proclaiming the Q and A segments are on, if you have any kinds of question, then feel free to ask us through comments. But before then, let's have a quick hear about the outlines of today's presentation. Actually, we started from the observatory. The first observatory was summer camp in the year 1420. We have come to know about the two kinds of observatory: telescope on Earth and observatory in space. We've come to know about the atmospheric capacity and telescope, ground and space-based telescope. We've come to know about the stars, its born, life, die, and it has, of course, a life of cycle. The sun has a sign. I've come to know about the region of sun's core. The first region was the core radiative zone and the convective zone, and some well-defined boundaries. The most important term of the solar model was the opacity. I've come to know everything the constituents of matter, abundance of heavy elements in space, basic elements of life, life servers and massive stars, universal element for motion, red sun, star, planetary nebulae, white dwarf, end of life. All these things we have come to know about, and we have come to know about our sun, some important points: solar flare, solar spot, solar wind. And we have moved into the theoretical proposition: start of spectral iron, satellite lamps in solar storm, a discrepancy in the study of pulsarization of CP8 variables, opacity project and the iron physics, plasma opacity, they found in solar opacity, radiation, atomic process in plasma, solar spectra, absorption and emission lines, solar spectrum as seen from there, iron of the sun, photoionizations, a lot more things about the photoionizations. And one wonderful thing was from this presentation is the creation of the sun at Sandia National Laboratory, and comparison of iron opacity experiments and theories, and the comparison resonance effect on photoionization and inherence in iron. And we have a book here, the textbook, which has made a bridge between physics and astronomy. The name of the book was Atomic Astrophysics and Spectroscopy. So thank you very much, ma'am. And now I am taking some questions from the audience.
I'm surprised you captured so many. I'm so pleased. I'm very happy. Pray all the best for you. Smart boy.
Thank you, ma'am. Thank you. First question, please.
Oh, origin of our photon in our sun? Okay, good question. So photon actually, you can say at the center of the sun, we have nuclear fusion, and during that fusion, part of the mass converts into energy, gamma rays. So when the gamma rays pass through the radiative zone, convection zone, they excite the atoms, and so that is absorption. And then when it gives de-excited, it gives out the photon. So you can say that the origin of the photon is when atom excitation. Okay, the one we see is due to atom excitation. So now when we study the star, so the atoms are around, atoms and ions, they get excited and then they drop down. When they drop down, the photons are given out.
Okay, thank you very much, ma'am. The next one was from April.
What?
Actually, what keeps the sun spinning? Does the sun rotate clockwise or counterclockwise?
Okay. So everything is in motion now to balance things, and now we just moving. So the plasma is moving, so that is causing the spin because everything is moving. There's not, and it's a plasma. There's nothing fixed holding it there. So when plasma is moving, it is also moving. So it's rotation clockwise or counterclockwise. It could be counterclockwise because I'm just assuming it is counterclockwise because our Earth is counterclockwise. Everything is counterclockwise. The planets are going counterclockwise.
Okay.
Electric current in the sun?
Next one, please.
Oh, okay. Because electric current means motion of electrons give you electricity, right? And the sun has largely, it is a plasma, so it is as charged particles. So charged particles is current. So yeah, it's a huge amount of current is being produced on the sun or in the sun all the time.
From Deepa Mondal, she wants to know how often does the sun's magnetic field flip?
Okay, in general, in every 11 years, when you accumulate a lot of solar spots, the whole thing just flips. So it has been seen that on the average, it is not exactly 11, but on the average, every 11 years.
Next one from Anup Malakar. Why is it important to study sun?
Okay, that's how we started. Sun is our star, and without the sun, we cannot survive. It is the source of energy for us. Okay, and so the dinosaur died because sun could not penetrate the atmosphere. Right, the dust was around the earth when the meteor hit the earth, and they died. And we need to warm up. Our body needs heat. We need to produce food and all. So that is the source. That's why it is important to study the sun. What is going on with the sun. Anything is happening, we have solar storm, we have to study that. We have why you have communication interruption, or when should you expect a huge amount of charge, particle, or radiation are coming. So how to protect ourselves. So we have to know. The more information we know, the more control we have, right? And the other one is that if we want to study objects in the space, the all are standard, just like sun. So if we know sun, then we can, and it is the closest one, right? Then we can study other objects. At this time, we always compare or use the data of the sun to study other stars. So you have to use accurate data to know get the accurate information of other stars.
Okay, next one from Shamim Reza. How long does it take for black dwarf to complete?
Very good question. I don't think we have detected any yet, because we have white dwarf. Okay? Most of the white dwarf we have detected, that is still giving out light. Okay, so they are cooling off slowly. Okay, and this cooling off may take long time to become black dwarf. So far we have, so it will take probably, I would say, billions of years.
Anup Kumar Paul, what is plasma? How does it form the sun core?
Okay, plasma means when it is a state when you have a matter, like not solid, or not completely gas. It's kind of in between, but the particles have charge. So it is not a neutral medium. It's a fluid. It flows, and so that is a plasma. When you have charged particles in it, we call it plasma. And how does it form in the core? Okay, this plasma, well, they are so dense and so hot that the plasma remains plasma. All the stars are made of plasmas. So because it's very hot, because they are compressed, and due to gravity they collapse. So there are a lot of energies involved. So that's how it is formed. And not in the core they fuse. Plasma is all around the sun, but in the core, the plasma, they are so compressed that they fuse to form heavier elements. Which are known as dark matter. Okay, dark matter is a different issue. Okay, so dark matter, as we know, dark matter is something. When we say dark, that means we don't know. Okay, but we know it exists. For example, we see a motion of a star, just for example, going around. It should not have that kind of motion. We can tell if it's going circular, but as if there's a gravity, something is interrupting its motion. So then we know something is there. Some matter is causing the change in the motion. So that's why we detected dark matter. We cannot detect directly, but we detect it from the motion. So at this Earth, we know the universe is expanding. And why it is expanding? Because we say dark energy, something we cannot explain also, is pushing things out. But what is keeping them, but why the motion is slower? Because there dark, some matter is there, which is also like keeping the motion slower. So that is what dark matter. People have all kinds of ideas about dark matter, but we don't know exactly what is, baryons or electrons all together. But it is still under study, but it exists in large amount. Could you please tell us about the project Artificial Sun? Is it really necessary for us? I'm not very much familiar with artificial sun, but we do want to study sun. Of course, anything we know is good for us. So the thing we produced in the laboratory in Sandia National Lab is created a very small amount of plasma which simulates the plasma inside the sun, which we are not able to do in the past. So yes, of course it is necessary. We are not going inside the sun. If we want to study, we have to create something on the earth which can simulate and we can study. As I said, the sun will die someday. Maybe we are surviving, but human race has to survive, right? So they have to continue to live. So that means we have to know what is going with the sun. Ultimately, we have to move to exoplanet. We are far, far away in technology to reach that goal. So we have to move on, we have to keep our science into advancement, develop technology, understand more science. You have to keep on doing it. We did not come to Earth just to eat and live. Right now we have technology. You cannot, we should be thankful who brought the technology from the past up to this time. It is our duty, your duty, to continue it so next generation can get more information. Is it possible for the sun to create aurora at other planets? Of course, why not? If that planet maybe it is created in the Mars, who knows? Now, if the atmosphere is there, Mars has very thin atmosphere. If it is aurora is what? It is just the charged particles trying to moving, and it is colliding with the atmosphere of the planet, and it is as it burns. When the particles burn, then it gives out the light. That is aurora. So it can happen. And a solar wind, I think, goes up to Mars. It may have to go up to Mars. It goes quite far. Beyond the Earth. If it is going there, yes. How can you identify element by its photon emission? Very good question. All right. See, each element has a particular set of photons coming because they have fixed orbits. Each element has separate orbits. So each orbit means, we know the energy difference between the orbits. That's what we study in the lab, also theoretically. So we know exactly the photon, will come out from a particular element. So whenever we catch a photon from the space, we compare that photon with the known data. So if we see that photon matches with the photon of iron, we said, okay, this photon is coming from iron. Because we study spectrum and publish it so that it is available. There's this website, it's called NIST website. NIST means National Institute for Standards and Technology. It's a US government institute whose purpose is to give very accurate numbers. So they have these photons listed, in the websites for each element and ion. So you have oxygen, but oxygen can have 8 ionization stages. So all those are available. Some of them are not available, but people work on, I do work on, we publish. So they are also in publications and literature. Another question, how is it possible to form diamond from hydrogen, helium, and other gaseous elements in the white dwarf? Well, they don't form from hydrogen, helium, and other gas. The diamond is carbon, crystal carbon. Okay, so what we have carbon in the white dwarf, lot of carbon. Okay, so they are very much compressed. When you have like loose carbon, it can be amorphous. They are not crystal. Like the pencil has that. Graphite. But if you press them, they form structure, crystal. That is diamond. So hydrogen helium means they have to fuse to form carbon. Only then diamond can form, and they already form carbon. Professor, what the current such project you are working on right now? Okay, I'm working on, of course, the sun. I've been working on the sun for a long time. Also, I'm working on exoplanetary spectroscopy. That means, if we can find the life in the other planets. So this is another project that I've been working on, detecting something which will tell you maybe there's a life form in that planet. So that is one thing. I'm also studying something called, you heard about black holes merger. So following two black holes or neutron star, they merge, and following during the merge, some of the mass converts to lanthanides. So I'm also studying that set, lanthanides from merger of black holes and neutron stars. And also I study, as I showed you, a planetary nebula atmosphere, all of those objects. Implicit about Parker spiral. I'm not sure about Parker spiral. Probably you know more than I do. There's so many things to learn. The name sounds familiar, but I don't quite remember. Maybe you can tell us.
Okay, I won't take any more from the audience. There are a few more questions, but it's too late. Okay, thank you very much, audiences. I was at final points of our program. Where the topic of our program was the study of the sun through atoms. If you want to know about the atoms, then I think that you need to have some knowledge about atoms. And if you study the course of atomic and molecular, I think that it is in the plan of the course plan of Department of Physics in Bangladesh. And if you know about the behavior of atoms, I think that you need to have some knowledge about quantum mechanics too, which has been shown in the presentation from Honorable Professor. Okay, we're just above the completion of our program, but before then, that's just a quick words from you.
All right, so we are finishing the program now. Okay, first I'd like to thank everyone for staying up late. We started late. There are some technical problems, but I like the question that you paid attention, and I really appreciate listening. And it's something that we need to continue. You need to continue. You are young right now, and I pray that all of you become well known in your field, and make advances, contribute to the advances of science and technology, and so that we have more control of the things going on around us. Okay, and Allah bless all of you. Thank you.
Thank you very much, ma'am. It was a motivation who was just enthusiastic and interested in astronomy. And ma'am is working in STEM project in India, and we have observed actually women in STEM in 11th February. So once more, girls and women to be very much enthusiastic in science, technology, engineering, and mathematics. So hopefully we'll get you once again, ma'am, in the new webinar with new topic, and it's a very thank you very much actually from the core of my heart on behalf of the Jamrul Islam Astronomy Club, Joshua Science Technology. Okay, see you again with a new webinar and with a new topic. Till then, it's goodbye from here and keep learning astronomy.
All right. Allah Hafiz and Assalamu alaikum.
Allah.